Hello everyone, my name is Milos Prvulovic. I'm a professor at Georgia Tech and I'm here to present our work, Nonce, which is a single trace electromagnetic side channel attack that we have applied to constant time ECC on mobile platforms such as phones. This work is a collaboration with our students, Monjur, Baki, Yilmaz, and Werner, who are from Georgia Tech, Niels, Samwel, who is now at Radboud University, my colleague Alenka Zajic, who is also at Georgia Tech, and then Daniel Genkin from University of Michigan and Yuval Yarom from University of Adelaide. The motivation for this is that public key cryptography is essential for modern security. It's needed for secure exchange of session keys. It's used to verify identity of systems and of users, and much, much more. Private keys for public key crypto are a highly valuable asset, so attackers want to get them, and we don't want the attackers to get them. So a well-designed public key cryptography like ECC is designed to make private keys very, very hard to recover if somebody knows the signatures and the messages, for example. So here we supply the key to ECC, a message digest comes in, a signature comes out, and if the attacker can observe this message and the signature, the attacker still cannot recover the key. So the attacker cannot sign additional messages of their choosing. This should be true even if there is lots of messages and corresponding signatures that the attacker can obtain. Analog side channel attacks, however, exploit the fact that cryptographic implementations run on real hardware. That is, there is switching in logic gates causing current flows, causing EM fields, and so on. And because of that, the attacker gets additional information, not only about, let's say, the messages and signatures, but also about some things that are going on inside of this ECC black box. And most side channel attacks like this can eventually recover the private key by using this information. Our attack, Nonce, allows the key to be recovered from only one signing operation, which makes the attack particularly dangerous. Before we go into how our attack works, let's first briefly review the ECC digital signature algorithm, where we have the D, which is a scalar that is the secret key, and it's multiplied with the generator point of the ECC algorithm to essentially get Q, which also acts as a key. Then we get the hash of the message, and then we generate a random secret K, the nonce, which is ephemeral. That is, it's only used for this particular signing operation, but it has to remain secret, as we will see. And then we multiply that nonce with Q, which is an EC point, to get another EC point R, and then R is essentially massaged into becoming the signature. The key point here is that if the attacker knows K, a message and its signature, so essentially if we know the K with which the message has been signed, then it's trivial to compute D from the knowledge of the signature message and the K. And that means that the nonce K must remain secret if the safety of the algorithm is to be preserved. The key operation here is this K times Q, multiplication of the EC point with the scalar K that must remain secret, and that's what we will be attacking. So this point-by-scalar multiplication, the K times Q, is computed using essentially the grade school algorithm in binary. That is, we start with a 0, and then for every bit of the scalar, we double the point, and then if the bit of the scalar is 1, we essentially add Q to the result. However, this conditional add here is a problem because it allows many kinds of side channel attacks such as flush and reload, because this R equals R plus Q is only done when the bit is 1. To avoid that, a constant time implementation is needed, and one possibility there is essentially to do this addition of the elliptic curve points R plus Q all the time, putting the result in a temporary, and then we conditionally swap the result and the temporary depending on the bit. Now, of course, the swap cond also needs to be done in a particular way to prevent it from just having another if then else. So the conditional swap is done according to RFC 7748 by essentially computing a mask that depends on the condition, such that it's all ones or all zeros depending on the bit cond. And then for each machine word of the EC point, what we do is we basically compute this delta, which is the difference between the two words, but we condition this delta using the cond such that the difference ends up being 0 if the cond is 0, and it ends up being the actual difference when cond is 1. And then what we do is we basically XOR the words of the 2 points with this, effectively XORing them with 0 if there is no swap, or XORing them with the actual difference for the swap if there is a swap. Note that this is also constant time, but for our attack, what we notice is that there is about 40 XOR operations here with the same operand delta in the swap conditional. And all of these operations have a 0 operand delta when the condition is 0. And all of them have a non-zero operand that has about 50% ones when the condition is 1. So now we collect signals for the attack by basically placing a small probe next to the unmodified phone that we're attacking, and then recording the signal that the probe collects using a software-defined radio, which is the white box that you see here in the pictures. Okay, so we got the signal. Now we need to find where the conditional swap part of the signal is. As you can see, there is a conditional swap, and then there is a double and add for each of the bits of the scalar. And the double and add takes a lot more time, and it's also highly recognizable. So it's pretty easy to identify which parts of the signal are this conditional swap for each of the bits. So now, zooming in into this conditional swap, if we look at its signal, we can see that there is a clear difference between the signal when the condition is 0 and when the condition is 1, and that's what we exploit to basically tell for each bit whether it's a 0 or a 1. And this is just to illustrate that in all 4 implementations, although their code is slightly different, all of them have this difference between zeros and ones in the con swap, produce slightly different signals that can be exploited for the attack. So our nonce recovery algorithm consists of basically training a priori by recording the signal while signing with a few known nonces on a device of the same kind or on the same device, and then clustering the training conditional swap signals using the k-means clustering algorithm and labeling the clusters. To attack, we record the signal from the target device, we identify where the signals that correspond to con swap operations are, and then we label each of those snippets according to which cluster from training they're the closest to, and that way we get to almost all of the bits. The few bits that we don't get usually are not wrong. Usually what's happening is that we couldn't identify where the snippet was, and that means that we essentially have an erasure, so we can just brute force what the missing bits are, and usually there is very few. And in our experiments, we showed that bits 0 and bits 1 are actually very easily separable using the training. So pretty much we can easily tell them apart and know which are ones and which are zeros. Some of them are missing, but as this distribution here shows, it's up to 15 bits missing, which means it can still be easily brute forced. And this is just for GnuPG on ZT. Other implementations on other phones are even easier for us to recover the nonce. Okay, so the attack works, which means we have to mitigate it. The mitigation goes after this fundamental enabler of the attack, which is the repetition of all zeros or all 50-50 numbers in each of the swaps. And the mitigation essentially introduces randomization to avoid this amplification. Pretty much the delta in the conditional swap is now going to be a 50-50 zeros and ones number, regardless of what the value of the condition is. So the mitigation takes the original swap conditional and then changes it such that there is a random number now that is XORed with the delta, such that the delta that we will use to XOR with the words is unbiased. It's always 50% zeros, 50% ones. And then we XOR additionally with the original random number in order to undo the randomization. What this does is it essentially removes the systematic bias towards 0 when the condition is 0. This mitigation happens to be optimized out by the compiler, so we need to additionally get the compiler not to remove the mitigation, and the details about this and more about the mitigation are in the paper. So before the mitigation, we have this nice clustering where zeros and ones are easily separable in all 4 implementations, and then after the mitigation, we can see that zeros and ones are now indistinguishable from each other, so pretty much the attack now no longer works. So to conclude, Nonce at-once is an analog side-channel attack on constant-time ECC implementations that use conditional swap from RFC 7748. It's a highly accurate attack thanks to it exploiting leakage amplification, and it's successful on all 4 implementations that we have tried. The ECC private key is recovered from only one use of that key, which is a problem, and our mitigation involves randomization of the con swap such that the leakage amplification is removed, and this mitigation has a very low performance overhead. Thank you, and now I'll take some questions.